So the second thing we're going to be talking about today is angular momentum. Now, it should come as no surprise to you that angular momentum is the rotational equivalent of ordinary momentum, and it follows the same sort of rules. So just like ordinary momentum would be P equals mv, momentum being mass and velocity, and governs how objects behave in collisions and such like, it should be no surprise that angular momentum is rotational inertia, the rotational equivalent of mass, and rotational velocity, the rotational equivalent of velocity. And we've given it a nice new letter, L. And its units are kilogram metres squared per second. Now we can do exactly the same sort of things with angular momentum as we can with ordinary momentum. So we can work out how much momentum something has as it travels, when it gains speed, and so on and so forth. We can even have the same impulse or a similar impulse equation where we can look at the change in angular momentum in terms of the torque and the time. So you'll still be solving problems where you change something in a collision, or you apply a torque for a certain amount of time and you're looking for what happens to it. Now, angular momentum is conserved during a collision if there's no external forces, just like ordinary momentum is. It's still conserved during a collision. If there's no turning force applying, it's a conserved situation. Now, the classic examples that we're going to see over the next few lessons are things like helicopter tail rotors. We can now explain why helicopters have those rotors on their tails, and we can explain it using a physics understanding. How fast do they have to spin to keep the angular momentum constant, for example, or stop the helicopter from spinning the other way? So, figure skating. So, you know when you see figure skaters go into a spin, and when they put their hands in close to their body they turn fast, when they put them out they turn wide. Well, we can explain that now. When a person is spinning and they put their arms out, they've changed the distribution of their rotational inertia. And diving, you know, when we watch figure diving and we can see the person turning with your arms out versus turning with your arms in. So we can now explain all of these in a mathematical and physical way, not just in our kind of understanding of what's happening. Now, the last thing that we're going to have to cover in this unit, it's called angular momentum of a particle, and I like to think of this as pretty much just the same as what we've looked at before. We've said that, that theta, the angular displacement, is related to d, the linear displacement. We've said that v, the linear velocity, is related to omega, the angular velocity. And in each case, we've said the scale factor is r, where the thing is, or where you are in relation to the turning or the pivot point. So it should come as no surprise to you that angular momentum and translational momentum can also be connected by the radius. Now, a lot of scientists will talk about something as if the straight line object, the translational object, has angular momentum. And some of the examples they give are things like, you've got a stationary merry-go-round, and here it is, we're looking down on it. A person runs along and jumps onto the merry-go-round, and the merry-go-round will start turning. Okay? And we can say, well, that person, when they jumped on the merry-go-round, they must have had angular momentum. I don't think that's necessarily the most helpful way to think of it, but if you like it, you roll with it. I prefer to think of it as they translate their linear momentum into angular momentum when they collide with the merry-go-round. So this has a nice simple formula where the angular momentum is mv, the momentum of our little person running, and where they land on this roundabout, this merry-go-round rather. And you can see that a person running with the same mass and the same speed, if they land out here, they're going to cause a lot more angular momentum than if they run and jump in here, closer to the centre. And we're going to solve some problems about that as well.